the real benefit to the idea of potential flows is this idea of superposition. It's a very powerful idea that allows us to build up solutions to very complex problems by building on the solution of our simpler problems. So the idea here is that our velocity potential satisfies Laplace's equation. Laplace's equation is a linear homogeneous PDE. So that means if we have two velocity potentials, we can add them together, and the sum will still satisfy Laplace's equation. So what we can do is take elementary building blocks, elementary plane flows, and build them up into more complex and interesting flows that we can analyze. And we're going to demonstrate this with a couple of examples. If we want to model a pipe discharging into a river, we can look at a uniform flow, which represents the river, and a source, which represents the pipe that's discharging. So we add up the uniform flow and the source potentials. Now here we have an xy term and an r theta term, so we need to convert coordinate systems. So we convert x into r cosine theta, and this gives us polar coordinates. And then we can take the derivatives here to come up with our velocities. And we can integrate the velocities to find the streamlines. And so what we end up with is we can plot the streamlines. And the solid line here indicates what could be considered a solid boundary. No flow crosses it. So this could be what's called a Rankine body, or a half Rankine body, where you have this solid shape inside of a flow. It also can represent the behavior of a uniform flow plus a source where you have water, and then you have to look at the velocity streamlines and so on inside that solid black line as well. We can also look at a tornado as a combination of a sink with a free vortex. So we add those two potentials together, we obtain the velocity field. From the velocity field we can get not only the streamlines but the pressure field from Bernoulli's equation. So we can actually look at the pressure inside of the tornado using the velocity potentials. And so we can see in this graph the point is going to follow this line as it circulates towards the center, where it's going to be drawn out of the system by the sink. If we want to look at a solid cylinder in a flow, we can actually combine a uniform flow with a doublet. Again, we have to convert the uniform flow into polar coordinates, but we can do that. And then we simplify the equation to obtain this simplified form. Now, it's interesting to note that this a squared depends on the strength and the velocity of the uniform flow. And when we plot this, you see this solid black line, that represents the surface of a solid cylinder. No flow goes through that. And so the radius of that circle is A. So we can get the radius of the circle A with the strength S and the velocity of the uniform flow U. Or we can work backwards. If we have a uniform flow and a cylinder that we want to model, we can use that to calculate A and put this into our velocity potential. Now, if we are looking at a solid cylinder, we just ignore what's going on inside that black line. Now, this doesn't seem too helpful. I mean, we don't usually see cylinders in viscid flows in real life. However, there are some important consequences to this model. We can actually add a layer of complexity by adding a vortex. So this is a rotating cylinder now. Now we have our uniform flow, our doublet, and our rotating vortex. And when we do that, we come up with a new equation, which is very similar to the cylinder, but now we have this rotation part. And we can graph the streamlines. And you can note that there's some stagnation points on the surface of that cylinder. And then we can also see that on the upper side of the cylinder, the streamlines are closer together. That means the velocity is higher on the top side of this cylinder than on the bottom. And since the velocity is higher, then the pressure is lower. Since the pressure is lower at the top than at the bottom, there's going to be a pressure force upward on this cylinder, and that's lift. So this idea is very important for aerodynamics. We can apply some mathematical transformations to this problem and use that to calculate the lift on an airfoil, like an airplane wing. You could use something similar in 3D coordinates, and you could find the lift on a spinning baseball or a spinning golf ball. using inviscid flows. Now, while these ideas are powerful, there is a shortcoming. In 1752, D'Alembert's paradox was first expressed. In potential flows, there's no drag. If you look at the cylinder example that we used, there's no drag on the cylinder using the idea of potential flow analysis. Now, from practical hydraulics, engineers know that there is drag on pretty much everything. So our theory predicts no drag, but our experiment measures drag, and that's a problem. It almost invalidated the whole fluid of fluid science until 1904, when Prandtl developed the idea of boundary layer theory. And that's going to lead us into our next module. But boundary layer theory accounts for viscous effects in the no-slip boundary condition. Today we mostly use CFD analysis for this type of problem. But in the past, they didn't have those tools, so they had to use some of the approximations that we're going to talk about during our next module.